In taking a look at where we are today, it often is helpful and useful to take a look at where we've come from as well. For example, in the old days, when we started working with networking, we used coaxial cables. So we had these coax cables with terminations on each end, and we'd use these little T connectors to connect each of the computers with their network adapter cards to this coax cable. And what this represented was one common network or one common bus that everything was connected to regarding the network. And it was a lot of fun. But there were some problems with this, including the fact that if we had a break in the cable, for example, right there, the whole network would go down. Well, it wasn't too many years after that they came out with hubs. And this is an example of a hub. And here's a graphical representation of the icon for a hub. And we can kind of think of a hub like a multi-port repeater. It simply takes the bits that go into one of the ports and it simply repeats them out all of the other ports. So if PC1 on this port right here is sending bits into the network, this hub, acting as a repeater with a whole bunch of ports, simply takes those bits and spits them out, repeats them on all the other ports that are actively connected. It's considered a physical layer or layer 1 device. And I remember being so darn excited about a hub because even though it acted like a logical bus where one device sends and everybody else hears, the cool thing was if we had a failure, maybe this cable broke or that cable had a problem, it would only affect those individual devices on those ports. It wouldn't affect the rest of the network. So with the hub, it was physically wired like a star. So we have our hub in the middle and then all of the devices connecting off of that hub. So it's physically wired as a star, but it logically acts like a common single bus because every other device on the network gets the opportunity to see all the bits being sent by any device. And one of the benefits of having standardization regarding networking technologies, including technologies like Ethernet, is that we have standards on MTU, which is an acronym for the maximum transmission unit. Effectively, how big a frame can be that's going to be transmitted on the network. If all the PCs on this network, if they're all playing by the same set of rules and standards, including MTU and voltage levels and so forth, it allows these devices to communicate, and we can buy a standard hub from pretty much any vendor at the time that made hubs. So even though we have better technology today, let's continue our discussion with a larger network that's still using hubs. Because these hubs, every time they receive bits on one port, repeat it to every other port, if a device on the network issues a broadcast, everybody connected to these hubs is going to see that broadcast. And that concept is a broadcast domain. So if all of these devices are in the same broadcast domain, that means or implies that if any one device sends a broadcast, everybody else in that same broadcast domain will be able to see that broadcast. Now, one of the challenges that comes up is what if computer 1 right here and computer 2 both decide that they want to try to transmit and send bits at the same exact time? And with these hubs, we have one giant collision domain that doesn't support multiple people talking at the same time. So one of the technologies that was developed to address the problem of two devices talking at the same time and running over each other is the technology called CSMA/CD. And that's an acronym for carrier sensing, which effectively means each computer, before it sends on the network, is supposed to listen and make sure that no one else is talking. Seems pretty courteous. Multiple access, the MA, that means there's multiple devices that may be accessing the network. And then the CD portion stands for collision detection, which means that if two devices are sending on the network at the same time, they'll see that they're walking on top of each other. Then they can back off, stop, listen, and they can try again when they think it's clear. So whether we were running on coax cable or using hubs, CSMA-CD was the technology that allowed it all to happen to that same network where those devices were in the same collision domain, which effectively means they had the potential or opportunity to collide with other devices who are also trying to send on that network. And CSMA-CD wasn't the only technology that was out there to facilitate multiple devices connected to the same network. There was also CSMA, carrier sensing multiple access, with collision avoidance. And the concept is a device, before it speaks, would send a little teeny frame, and if that frame made it okay, it knew it had a big enough window so it could send the full message and get it sent without a collision on the network. And one of the realities in current wired networks is that we no longer need to use carrier sensing multiple access with collision detection or collision avoidance on physical networks because we've swapped out, or we should have swapped out, our devices. Instead of using hubs, we're going to be using layer 2 switches, which are more intelligent and have some additional benefits, and we'll put those in a separate nugget. Before we close this nugget, I'd like to share with you one other concept regarding the types of traffic that we might send from a networking device. The first one is a broadcast. So let's imagine that computer 1 is sending a broadcast into the network that's intended to reach and be communicated to every other device that's in that same broadcast domain. However, if we have a server that's generating multicast traffic, multicast is intended to go to a group of computers. Not all of them, just a portion. So if the intended audience is, for example, computer 2 and the wireless device, who are part of a multicast group, that's an example of multicast traffic. Traffic that's intended for a group of computers. And then last but not least, we have unicast traffic. Unicast traffic is traffic that's intended for one other party. A user at this branch office right here, let's say that's Lois. Let's imagine that she's connected to a printer. When she sends that print job to the printer, that traffic is intended for just that one device. Not a group, not a broadcast, but just one device. That would be an example of unicast traffic. If you and I went into business and we manufactured network cards that plugged into Ethernet networks, one of our responsibilities in building and manufacturing these cards would to make sure that each of our network adapters had burned into it or programmed into it a 48-bit unique address that network adapter could use as it communicates locally on that network segment. One of the uses for a layer 2 address on a network adapter is that it allows a unique way of identifying that adapter on a network segment. And these layer 2 Ethernet addresses are 48 bits in length. But you know what? It's kind of a pain to talk about 48 bits between friends as 101100. It's just too tedious. So what we do when we represent those where humans are going to be reading it, we're usually using hexadecimal characters, 12 hexadecimal characters to represent those 48 bits. Another interesting phenomenon is that these layer 2 addresses have lots of different names, including names like an Ethernet address, or a layer 2 address, or a physical address. Even though this is a layer 2 type of function, because the addresses are going to be part of the layer 2 frames, I suppose because they're burned into some of the network adapters, and a network adapter is a physical thing, it got the term physical address. But in any case, all these terms and names are referring to the layer 2 Ethernet address. And while we're doing name calling, another name that these are often referred to as are MAC addresses, capital M, capital A, capital C, where that MAC doesn't stand for Macintosh, it stands for Media Access Control. And it's because we have these layer 2 addresses that intelligent devices like a layer 2 switch can take advantage of that information, for example, where this frame is coming from and where it's going to, because the source and destination layer 2 addresses are inside that layer 2 frame. So a switch can make intelligent forwarding decisions based on that layer 2 address information in each of the frames. And oftentimes, when learning something new, like for example, wow, there's a layer 2 address on my network adapter, it's often fun to take a look at what yours is. And so here's a couple of different ways, depending on the platform that you're on, that you can look at your layer 2 address. So let's begin on a Linux box. If you happen to be on a Linux box, the command would be ifconfig. It'll list your interfaces, and as part of that, it's going to list the hardware address, which would be one more name that we could refer to the layer 2 address as. So Ethernet address, layer 2 address, physical address, MAC address, or hardware address. They've also put some colons in to help separate 2 characters at a time. On a Windows platform, we'd go ahead and run the command ipconfig/all. So if you go to the interface you're concerned about, you can look at the details for that. And then just below that, here we have the physical address, which is that bad boy right there. Once again, it's represented by 12 hexadecimal characters, representing a 48-bit unique MAC address. And even if we're not on a wired Ethernet network, we still use the concept of a layer 2 address when working with Wi-Fi. So even on a mobile device, it's going to show us a Wi-Fi address, which once again is 12 hexadecimal characters. They've thrown in some colons there just to make it easier to read, and that represents a 48-bit layer 2 address. And if we're on a network device, maybe a router or a switch, we'd use the appropriate command there. So the commands may vary a little bit between Juniper and HP and Cisco. So here on this Cisco device, I'm going to issue the command show interfaces fast Ethernet 1/1, which will show us a lot of details regarding that interface, fast Ethernet 1/1, including the layer 2 address. So we'll press enter. So here, among a lot of other details, it's showing us the address is this bad boy right there. And so in this output, Cisco is giving us 4 characters and a period. So whether a vendor is using colons or periods to separate the numbers, they're doing so just to make it a little bit easier to read. And then one last thing that I thought would be fun to do is let's take a look at a packet capture in Wireshark to take a look at the layer 2 information and take a look at some Ethernet frames that are including both the source and destination layer 2 addresses in those frames. So we'll just pick this top one here. And here in the layer 2 information, if we expand that, and that's showing us regarding this ping request, I'm cheating a little bit by just seeing that it's a ping request right here. The layer 2 destination address in that layer 2 header, this frame, is this guy right there. And the source address, the individual that's sourcing this frame on this network, has this layer 2 address, this MAC address right here. And one of the big benefits of including the source and destination layer 2 addresses inside of frames is that a network device, for example, a layer 2 switch, can now look at those addresses and make intelligent forwarding decisions on the local network based on where that frame needs to go. It is a challenge to configure, troubleshoot, or manage a device if we're not sure how it works. So in this, I'd like to share with you the basics of how a layer 2 switch operates. So let's begin by introducing this topology. I'm really pretty proud of it. We have 3 PCs, PC 1, 2, and 3, and each of them are connected physically with a little patch cable that goes from their network interface card at their PC down to the port on this switch. So PC 1 is physically connected to port 1/1, PC 2 is physically connected to port 1/2, and PC 3 connected to port 1/3. Also, for this topology, I've assigned each of the PCs a network layer address, and that's these top numbers. PC 1 can be reached at 10.00.11, PC 2 at 10.00.22, and PC 3 at 10.00.33. I've also included the layer 2 MAC address, or at least a portion of it, for each of the computers. Because it's 12 digits long, I thought I'd just go ahead and put an x.x for the first 8 characters, and then write out the last 4 digits, which I've done here. So PC 1's MAC address, its layer 2 address, ends in 6800, PC 2 ends in 6801, and PC 3 ends in 6802. So now that we've been introduced to the topology in this 3-node network, let's talk about what this switch right here does for a living. So we've plugged it in, it's powered on, and one of the first things this switch is going to do and continue to do is to listen to the frames as they come in and learn. And the question might be, well, what exactly is it going to learn? Well, it's going to learn the MAC addresses on the PCs or other devices that are connected to its ports. And the way it does that, it pays attention to the source MAC address. And let's use PC 1 as an example. Let's imagine that PC 1 is sending a frame of data bit by bit into the network through this port on the switch. And it just so happens I had conveniently available a packet capture showing the layer 2 information that PC 1 would be using if it was communicating with PC 2. And just to give a clear picture of what's happening, PC 1 is doing a ping here. It's sourcing it from its IP address of 10.00.11, and it's pinging over to 10.00.22 right here. Now that's the layer 3 information, but at layer 2, that corresponds to the source layer 2 address of the MAC address ending in 6800, this guy right here, going to the destination MAC address of 6801, which is this guy right here. So as PC 1 sends this frame into the switch, from a learning perspective, the switch is looking at the source MAC address on the incoming frames, because the switch is curious and wants to know where all the MAC addresses live. So in short, when PC 1 sends a frame into the network and includes its source MAC address, the switch is going to build a table. It's going to say, okay, MAC address x.x. at 6800. That MAC address, because I saw it come in on port 1/1, is associated with port 1/1. So once these devices have all sent at least one frame into the network, which includes their source MAC address, the switch is going to have learned and then put into a table all their MAC addresses and where they can be reached. So regarding PC 2, the MAC address is XX6801, and it's associated with port 1/2. And for PC 3, it's MAC address that ends in 6802 on port 1/3. So the major concept is that the switch is listening and learning regarding the source MAC addresses for all the frames that enter its ports. And then secondly, it's building a table, so if it ever needs to forward a frame to any of those MAC addresses, it knows exactly which port it should send the frame out to reach that destination MAC address. And one of the beautiful things about a layer 2 switch is that it can do intelligent forwarding. Case in point, if PC 1 is going to send a frame to PC 3, it can craft that frame with PC 3's layer 2 destination address, and when that frame goes into the switch says, I know where that MAC address lives that ends in 6802. It's off of port 1/3, and it can forward that directly to that port and forward it to PC 3, and that traffic never even had to bother PC 2 at all. It wasn't for PC 2, PC 2 didn't care about it, and we're not interrupting anybody else except for PC 3 who's going to receive that frame. And if the switch is just powered on and hasn't learned where everybody lives yet, and it receives a frame, let's imagine that PC1 sends a frame into the network, the switch looks at the destination address, and the switch looks at its table it's built and says, oh, I don't know where that destination lives. The switch is going to err on the side of caution, and it's going to forward that frame out every other port where there's a device connected, with the hope that whoever that frame was for would have a chance to take a look at it. And what the switch is not going to do, it's not going to bother forwarding the frame out the same port that it came in on, because that would be silly. If PC1 is sending a frame, PC1 already knows about that frame. So a frame coming into the switch, where the switch does not know where that destination MAC address lives, is forwarded to all other ports. And that same kind of activity happens if a device sends a broadcast into the network. Let's imagine that PC3 sends a broadcast frame into the switch. A broadcast is also going to be forwarded out all other ports because it's a broadcast. Somebody might need to see it. So the processing of an unknown destination address and a broadcast are handled the same on a layer 2 switch. They're sent out every other port except for the port that that frame came in on. I thought it would be useful to demonstrate the actual process of a switch learning the layer 2 addresses of the devices that are connected to it. And although the vendors vary and the commands may be slightly different on displaying information about the dynamically learned MAC addresses, the concept remains the same regarding the layer 2 switches learning dynamically the MAC addresses of those devices that are connected to the switch. So in our topology, we have these 3 PCs on these 3 ports on the switch. And these 3 PCs have these respective IP addresses at layer 3, and they have these 3 respective layer 2 addresses, or at least the last 4 characters of those MAC addresses at layer 2. So when we start off, if these PCs have been absolutely quiet, not one single frame, we can look at the MAC address table, and the switch, if these PCs have not set any frames, should not yet know about any of their respective MAC addresses on any of these ports. However, once we generate some traffic, we should be able to go back and see that this table is being populated. So we're going to begin on the switch. Now this happens to be a switch module. That's a module inside of a router, a Cisco router. And so based on even the type of Cisco switch you have, the commands may be slightly different to show the MAC address table. So on this switch module in this router, the command to show the MAC address table is show space MAC-address-table. So we'll enter that and press enter. And at the moment, the switch knows about itself. It has a management interface, but it hasn't dynamically learned about any of the PCs that are connected to ports 1/1, 1/2, or 1/3 yet. Let's fix that right now. Let's bring up a console window for PC1. And if we simply do a ping of PC2 and a ping of PC3, if they reply back to PC1, that's going to allow the switch to learn all 3 devices' MAC addresses, because each of the devices, when they respond and use their source layer 2 MAC address, the switch goes, boom, gotcha. And it'll add that to the MAC address table. So here on PC1, let's do a ping over to 10.0.0.22. That's the IP address of PC2. That looks good. Let's also do a ping over to PC3 at 10.0.0.33. Press enter. That looks good as well. We'll let that complete. And then let's go back to the switch. And I'm just going to use the up arrow key to do the same command again to look at the MAC address table and press enter. And we can now see that the switch has dynamically learned 3 MAC addresses on 3 respective ports. PC1 ending in 6800 being learned off port FA 1/1 or Fast Ethernet 1/1. PC2's MAC address of 6801 learned off of port 1/2. And PC3's MAC address ending in 6802 dynamically learned off switch port 1/3. And the beautiful thing now is that if the switch needs to forward frames to any of those MAC addresses, it knows exactly how to do it, and it can forward those frames directly based on the learning it did, as opposed to just sending a frame to all other ports on the switch. To assist us in really appreciating the benefit of a VLAN, I want to talk for a moment about a layer 2 broadcast. Let's imagine that PC1 here is sending a layer 2 broadcast into this switch network. Now, from our previous discussions, do you recall what a switch does when it receives a broadcast in on one of its ports? What does it do? And if you'll recall, the answer is the switch is going to forward that broadcast, that layer 2 broadcast, out of all of its other ports. So that broadcast coming in on gig 0/1 on the switch would be sent out this port and that port and that port. And then when switch 2 receives that broadcast on its gig 1/0, it's going to forward it out every other port as well. So effectively, the broadcast that PC1 started is going to be seen by every single host on the network. Well, if we have 500 or 600 devices, and we have to see all the broadcasts from every other device. That is one reason to help limit the size of a broadcast domain. And the ability to limit or to cut down on the size of a layer 2 network is what VLANs do for us. A VLAN is a layer 2 boundary regarding how far a broadcast will go inside of a network infrastructure. So in our topology here, if we decided we wanted these two PCs, for example, to be in their own virtual local area network, and we wanted all these devices to be in a yet different virtual local area network, we could do that by simply controlling the ports on the switch. So we could put port gig 0/1 and gig 0/2 in the green VLAN, and we could put gig 0/3, and over here on switch 2, gig 1/1 and 1/2 and 1/3, all in the red VLAN. And that's how we control the layer 2 boundaries for our VLANs, for our broadcast domains. So if somebody walked up to us and said, hey, quick, tell me, what is a VLAN? We could say, it's a layer 2 broadcast domain. Ta-da! That's the full story. And normally what happens as well, when we start carving up our networks into virtual local area networks, not only are we going to change the VLANs that devices are in, but we're also going to change the layer 3 IP network that they're in as well. So if these guys are in the 10 network, we might need to change all the addressing on these hosts in the red network and maybe put them on the 20 network, for example. But we can save the discussion about IP addressing and how that works in detail for another nugget, because the focus here is on VLANs at layer 2, controlling how big a network can be, and doing it by controlling the switch ports. We've identified three basic things. Number one, the acronym of VLAN stands for Virtual Local Area Network. Secondly, we identified that a VLAN is effectively a layer 2 broadcast domain, meaning if our VLAN includes 14 ports and 14 devices, if a broadcast gets sent in on any one of those ports, it'll only be forwarded to the other ports in that same layer 2 VLAN. And third, we learned that we can control which individual hosts are in which VLANs by controlling the switch ports that those hosts are connected to. So if we have 16 ports on a switch, and we want 6 of those ports to be in one VLAN, and the other 10 ports to be in a second VLAN, that's done by configuring the switch and their respective switch ports to only be in those specific VLANs. To implement VLANs, we'd want to do three basic things. Number one, plan it out. We identify which hosts or which devices we want in which VLANs. Secondly, implement the changes. And then third, verify that it works. So as part of our planning, let's take a close look at our existing topology right here. We have 6 hosts, PC1 all the way through PC6. These numbers up here that start with 10 are currently their IP addressing information for each one of them. So PC1's IP address ends with .11, PC2 is .22, etc. all the way through PC6 ending in .66. And regarding these hosts, their connectivity to the network, their physical connectivity, is through these switches, switch number 1 and switch number 2. And currently, and by default in a Cisco network, all the switch ports are by default configured as being members of VLAN number 1. That's a little bit hard to read. Let me change the color there. So as part of our planning, let's decide that we want PC1 and PC2 to be in their own VLAN, their own layer 2 broadcast domain. So let's go ahead and put them into a new VLAN, and we'll use VLAN 777. So we'll create that new VLAN, and we'll assign gig 0/1 and 0/2 to that VLAN, which will then cause PC1 and PC2 to be in that VLAN called 777, and we'll leave everybody else in the default VLAN of VLAN number 1. So after we make the change at the switch ports, PC1 and PC2 will still be able to talk to each other, but they'll be isolated from the rest of the devices because the rest of the devices are in VLAN 1 while they'll be in VLAN 777. And for the demonstration, we're going to go ahead and walk through implementing this on a Cisco switch. Currently, all 6 PCs are in VLAN 1, and let's verify basic connectivity before we start making some changes. So here on PC1, let's go ahead and ping out to PC2, PC3, PC4, PC5, and PC6 just to verify that we have connectivity and that the network is currently functioning before. Great, so we verified some basic connectivity by doing a ping test from PC1 to the other 5 PCs. And currently that's working partly because every other PC is in the same exact VLAN, VLAN number 1 by default. Next, let's go to the switch number 1, and take a look at it. Here on switch number 1, let's take a look at the defaults that we have in place before we start making some changes. And on a Cisco switch, we can use the command show Vlan brief to take a look at the Vlan information. So over here on the right, we have a list of ports, and it's currently showing us here on switch 1 that gig 0/1, 2, 3, along with a few others, are all associated with this VLAN, VLAN 1, which is the default VLAN. And what we're going to do is we're going to take gig 0/1 and 0/2, which is where PC1 and PC2 are connected, and we are going to first create VLAN 777 and then put those two individual ports in that separate VLAN. So we'll go into configuration mode on this switch, and the first thing we want to do is go ahead and create our new VLAN. So we'll create VLAN 777, and we'll also give it the name of human resources. That way when we see it, we can know what it is. Next, we'll exit out of VLAN configuration mode. We'll do a quick show for the VLAN just to make sure that it exists. Sure enough, there it is. VLAN 777, named human resources. And at the moment, there are no ports assigned to it. And that's our next step. We want to assign ports gig 0/1 and 0/2 to that specific VLAN. So we'll go into range configuration mode so we can put in the commands for those two ports at the same time, and we'll use the commands switch port mode access, saying that we want these two ports to be access ports, followed by switch port access VLAN and the number 777, which is the VLAN we want them to be a part of. And having done that, we'll type an N to go out of configuration mode, and let's do a quick show command to verify our work. And we can do a show VLAN brief, and sure enough, we have VLAN 777, and now we have the two ports of gig 0/1 and 0/2 that are associated with that specific layer 2 broadcast domain. So our next step is to go ahead and test connectivity. We should have connectivity. In fact, let's go over to PC1. So here on PC1, we should have connectivity between PC1 and PC2. So we'll test that with a ping over to 10.0.0.22. That's PC2, and that continues to work. That's great. Next, let's ping 10.0.0.33, which is PC3. Now, because PC1 is in VLAN 777 and the PC we're trying to ping is in a completely separate layer 2 broadcast domain or separate VLAN, there's no connectivity without some other network device that's going to move our traffic over there for us. So this ping command is not expected to work. And sure enough, it is timing out. It's not working. However, if we go to PC3, here on PC3, which is still in VLAN 1, if we try to ping other devices that are still in VLAN 1, like PC4, PC5, or PC6, that should still work because those four PCs are all in the same broadcast domain, the same VLAN. So let's test it with a ping out to 10.0.0. And let's pick on 44, which is PC4, and press enter. And sure enough, that works great. But we won't be able to ping from PC3 over to PC1 or PC2 once again because PC3 is in a different layer 2 VLAN than PC1 and PC2. One rule about layer 2 broadcasts is that the broadcast needs to be forwarded to all other devices in that same layer 2 domain, that same broadcast domain. Well, what if we have two different switches that are connected together and we have a broadcast in VLAN 100, for example, on one switch? How does that switch, when it forwards that broadcast over to the second device, how does it let the second switch know that this is a broadcast for just VLAN 100 and not, for example, VLAN 200? Well, the answer to that question is solved with a technique called trunking and adding a little tag called an 802.1q tag to the frames over trunks. And one of the analogies that I learned decades ago, and is still pretty effective, is the one about airlines. And I've got 7 kids, and I care a great deal about every one of them. And when they were young, if I would ever have to send one of those kids on an airplane, we'd want to make sure that they got on the plane and were delivered correctly to the correct party on the other side. So what the airlines do is they create a tag with all the information for the child who's traveling alone, and they put it on that child for the duration of their trip. And then when they land on the other side, they use that tag that the child has on them to correctly deliver that frame to the right VLAN, or in the example of the plane, to deliver that child to the correct person who's going to take care of that child on the receiving side. So in our topology, we've got 3 computers connected to the first switch, we have a connection between the 2 switches, and then 3 more computers connected to the second switch. Also, the individual ports on their respective switches are carved out into various VLANs. The first 2 ports are in VLAN 100 on switch 1, and the third port has been configured to be part of VLAN 200 here on switch 1. And we have similar configurations over here on switch 2 with port 1/1 being in VLAN 100 and ports gig 1/2 and 1/3 being in VLAN 200. Also, to make things functional and work, we've also configured in this topology all the computers there in VLAN 100, their IP address starts with 10.100.0, and all the devices in VLAN 200 have an IP address that begins with 10.200.0. And the actual VLAN assignment is done based on the ports that these devices are connected to, and the IP addressing can either be done manually or through some dynamic process like DHCP, which we'll cover in a different nugget. But for now, this is how this network is set up. So if PC1 was going to do a ping request, so PC1's right here at 10.100.0.1, if it did a ping request over to PC4 over here at 10.100.0.4, when that frame goes in on gig 0/1, the switch, because gig 0/1 is configured to be a port in VLAN 100, the switch knows that that frame that's coming in is associated with VLAN 100. But here's the problem. When switch 1 forwards that frame over to switch 2 so it can get to PC4, it needs to add some information, a tag, if you will, along with that frame to indicate, hey buddy, it says to switch number 2, this frame is associated with VLAN 100. And that additional little information that it's adding is referred to as an 802.1q. That's the name of the protocol that does this, and is referred to as a tag. We're adding that information before we send that frame over to the other switch. And that way, when switch 2 receives it, whether it's a unicast frame or whether it's a broadcast frame, switch 2 will know right when it receives it, based on the tag, that this is a frame associated just with that specific VLAN, VLAN 100. And then as switch 2 forwards that frame up to PC4, it's going to remove the tag because it's no longer needed as it forwards the frame up to PC4 where that frame needs to go. So the play-by-play would be no tag here on the access port between PC1 and the switch. We'd have the tag added on this interconnection between the two switches, which is also called a trunk, by the way. And then when switch 2 forwards that frame out the port where PC4 is connected, that access port, there'd be no benefit or need to include that 802.1q tag because all PC4 cares about is the actual frame itself. And one of the big questions is, to tag or not to tag? That is the question. And the primary method that the switches know whether to include a tag or not include a tag is the type of port that that frame is going across. If it's an access port, which implies that we're connected to end user devices, devices that are not other switches or don't need to have that tagging information, those are referred to as access ports. And that's why when we configure VLANs, we configure both the type of port, whether it's an access port or a trunk port, and then if it's an access port, we also assign what VLAN that access port is a member of. So that way, when the switch is forwarding a frame over a trunk, it's going to add the tag. And when it's forwarding that frame over an access port, it won't bother including the tag. And to reinforce this and have some fun with this, here's a quick little snippet from a Wireshark packet capture of the frame as it went over the trunk when PC1 at 10.100.0.1 was doing a ping request over to PC4 at 10.100.0.4. And once again, the capture was taken over the trunk link. And as a result, here we have the layer 2 information with the source and destination layer 2 addresses. And then it wedged in here this next little piece, this additional little piece, which is the 802.1q tag. And in that tag, it includes the ID, which is the VLAN ID. Effectively, this says, this frame is associated with VLAN 100. So if switch is out of voice, maybe they'd sound like that. So any frames associated with VLAN 100 that are going across this trunk link between switch 1 and switch 2, whether they're unicast frames for a specific host or whether they're a broadcast for all devices in that same VLAN, as those frames cross the trunk, they're going to get this additional little 802.1q tag so that the receiving switch knows exactly which VLAN that frame belongs to. In a separate, we discussed the concepts of an 802.1q Ethernet trunk, and in this, I'd like to walk you through step by step of how to configure the ports on switches to behave as a trunk. We get to leverage the same topology that we used when we discussed the concepts, so our primary job here is to go into the configuration on switch 1 and switch 2 to these two ports, gig 00 on switch 1 and gig 10 on switch 2, and specify that we want to use 802.1q tags and that protocol for trunking. And in addition to specifying the protocol we want to use for the trunking, we also want to tell these two ports specifically that they are to behave as trunks. And what I thought would be also fun is to show you the configuration for the access ports as well. So we'll do the whole thing in this demonstration, which includes specifying that gig 01 and 02 on switch 1 are access ports in VLAN 100, as well as switch 2's gig 1/1, and then we'll configure gig 0/3 on switch 1, as well as gig 1/2 and gig 1/3 on switches 1 and 2 respectively, that those ports should be associated with VLAN 200. We'll also specify in the respective switches that on these ports connecting them together, that they should use 802.1q as the protocol, and that they should behave as trunks. And so with the intent of this not being just a typing exercise, let me walk through all of the commands, and then we'll go ahead and put them into the switches. On switch 1, we're going to go ahead into configuration mode on the Cisco switch. Our first two access ports on switch 1 are going to be gig 0/1 and gig 0/2. So we'll configure those two access ports by going into interface configuration mode for both of them at the same time and using the command switch port mode access that specifies they're an access port, and then we'll associate those access ports with VLAN 100. Then we'll exit out of that range configuration mode for those interfaces, and then we'll go specifically over to gig 0/3 and do the same command there, switch port mode access, but on it, we'll specify that it's in VLAN 200. Then exiting that interface, we'll go over to interface gig 0/0, which is the connection between switch 1 and switch 2, and we'll specify that we want to use .1q as the trunk encapsulation with the command switch port trunk encapsulation .1q, and then the second command switch port mode trunk that takes out any ambiguity that we want this port to be a trunk. And then we can exit out of configuration mode and use the WR command, which is the equivalent of copy running config to startup config. And the benefit of that is so that when the switch reboots, it'll remember the configuration that we're providing it right now. And then as we scroll down and take a look at the commands for the second switch, they're right here. And they're all very similar commands. Working from the left to the right on switch 2, we're going to configure gig 1/0 to use .1q encapsulation and to tell it to go ahead and act as a trunk. We'll also go into gig 1/1, configure it to be an access port associated with VLAN 100, and then we'll go to the interfaces gig 1/2 and 1/3 to tell the switch that those two ports are access ports, and then also to associate VLAN 200 with those access ports. Then we'll end to take us out of configuration mode on the Cisco switch, and we'll do a WR for write to save that configuration so that when it reboots, the switch will continue to remember the configuration that we're giving it right now. So I'll move these commands over a little bit, and let's scroll up, and we'll grab all the commands for switch number 1 first. Right click, copy those, and then go to the interface for switch number 1, right click, which will go ahead and paste that all in. So there's switch 1's configuration, and let's go over to switch 2 and repeat the process. So here on switch 2, we'll go get switch 2's configuration, right click, put it in our clipboard in our buffer, and I'll simply right click here in the interface for switch 2, which will go ahead and paste it in. And I'll finish it off by putting in the WR to save the configuration to the startup config. And it is done. Now, the big question might be, okay, Keith, we configured some access ports, we configured the trunk ports, how do we verify it? Great question. We can verify the access ports that we configured. Here we're on switch 2. We can verify those by using the command show VLAN brief, and that confirms that VLAN 100 has associated with it gig 1/1, that port, and that gig 1/2 and 1/3 are associated with VLAN 200. So regarding access ports, perfect. Now notice here, as we show our VLAN information, it's not showing us in our list of ports, it is not showing us gig 1/0. And that's because gig 1/0 is not acting as an access port, it's acting as a trunk. And we have a separate command that we can use to see that. And that command would be show interfaces, or you can use a shortcut of int space trunk and press enter. And this allows us to verify that gig 1/0 is currently using the encapsulation of 802.1q and is in the current status of trunking, which is great news. And beyond just allowing that range of VLANs to go across the trunk, down here it's showing us that it's actively forwarding and allowing VLANs 100 and 200, which we're concerned with in our topology, to be allowed over the trunk. Any traffic from those VLANs as they go over the trunk are going to get an 802.1q tag, so that the switch that receives that information over the trunk knows exactly which VLAN the incoming frame belongs to. I'd like you to imagine with me that a device on the network is doing a ping just to verify basic connectivity to some other device on the same network. And let's imagine that it's this device right here, PC1, that's doing the ping over to PC4. Also, as part of that ping request, I have a little Wireshark packet analysis snippet right here that we can look at as well. Here it's showing us the layer 2 information with the source MAC address and the destination MAC address, which matches up with the MAC addresses of those devices. And then the protocol behind the scenes that's being used for a ping request is ICMP, the Internet Control Message Protocol. So here's my question for you. If PC1 crafted this ICMP echo request, which it did, how did PC1 know what the layer 2 address was of PC4 on that same network? And two ideas come to mind. Number one, it's just magic, that's the way it works. Or number two, it's using some type of a protocol, a set of rules that allows it to discover and learn what the layer 2 address is of PC4. And the latter of those two is true. And the protocol we're going to use that resolves or determines or figures out what the layer 2 address is of another device on the same network is called ARP. It's Address Resolution Protocol. And here's the basics of how ARP operates. When PC1 is getting ready to do a ping request, for example, to the host at 10.100.0.4, it's true that PC1 really is going to need the layer 2 address of PC4's network interface card so it can put that destination layer 2 address in the frame to send the ping request. So in its preparation for sending that ping request, it looks at its ARP cache. Sometimes it's also referred to as an ARP table. And in the ARP cache, PC1 is going to look to see if he's already learned the layer 2 address associated with that host at 10.100.0.4. In the event that the ARP cache is empty, or at least doesn't have the layer 2 address for PC4 here, what PC1 is going to do, it's going to send an ARP request. And that ARP request is sent from PC1 as a layer 2 broadcast. It's like an all points bulletin that everybody's going to see who's currently connected to and working in the same VLAN as PC1. In this case, it's VLAN 100. And in that ARP request, it's going to say, hey, I'm looking for the person who owns the IP address of 10.100.0.4, and if that's you, please reply back with your layer 2 address. I need it so I can forward additional frames to you. And the question I have for you regarding a layer 2 broadcast that's being sent into the switch, what does a switch do with a layer 2 broadcast? And we've touched on this at least once in a previous nugget. And if you said, Keith, I got it, it's going to forward that broadcast to all other ports that are associated with that same VLAN. In this case, it'd be VLAN 100. And that's absolutely accurate. So if we follow that logic, the switch would forward that broadcast out port gig 0/2, because that's part of VLAN 100. It would take a quick moment and consider gig 0/3 and say, oops, wrong VLAN. It wouldn't send it out to PC3, so PC3 wouldn't see it. But the trunk is supporting VLAN 100, and so the switch would tag it with an 802.1q tag and propagate that broadcast over the trunk link over to switch 2, who would receive it, and then switch 2 would continue to forward that frame to any ports associated with that same VLAN of VLAN 100. In this case, we only have one, so that frame would be forwarded out gig 1/1. So the 3 ports that are associated with VLAN 200, which are access ports, they would not get that broadcast sent to those devices because they're not a member of VLAN 100. So let's take a closer look at the ARP request, and we'll go ahead and expand the details down below. So in this ARP request at layer 2, it's sourced from the layer 2 address, the physical address or MAC address, whatever you want to refer to it as, of PC1. And we can focus on those last 4 characters as matching PC1's MAC address. And then for the destination address, this is what a layer 2 broadcast looks like in hexadecimal. It's all Fs. So we have 12 Fs. Each of those Fs represents 4 bits that are on, which is 48 bits all on. And so when the switch sees that, it says, oh, I know what that is. And then it goes to work to forward that broadcast to all other ports that are associated with that same VLAN. And as we take a look at the details regarding the ARP request itself, here's showing us the sender MAC address and the sender's IP address, which is PC1's address. The layer 2 destination address is the broadcast, and then it has the target IP address. So even though every device that's in VLAN 100 will have an opportunity to look at this ARP request, only the device that owns and is currently using the IP address of 10.100.0.4 will do a reply. And if we take a look at the next packet right here, this is the response coming back from PC4 back to PC1. And once PC1 gets that ARP reply, it's so happy about that information, it's going to go ahead and cache PC4's layer 2 address inside of the ARP table, also referred to as an ARP cache. And the intent there is, if we ever have to send a frame over to PC4 again, I don't have to do the whole ARP request again. I can just look at my ARP cache, and if the information is there, I can simply use it as I create new frames that are destined or need to go to Mr. PC4. Wouldn't it be awesome to be able to predict with accuracy things like sporting events or how a network's going to behave? In previous, we've taken a look at how layer 2 switches learn MAC addresses. We've also identified how ARP operates and also how broadcast operate in a layer 2 environment. So I thought it would be fun for you and I in this to leverage that knowledge and predict what the MAC address table might look like on a couple of switches after specific types of traffic have been sent over the network. So here is our topology that we've used in several other nuggets. It consists of 2 switches that are interconnected with the trunk, 6 PCs connected on access ports on those switches to specific VLANs, as listed right here. Also, the MAC addresses are right here for each of the devices, and I just put the last 4 characters to make it easier to write out and manage. I've also got the IP addresses, the layer 3 logical IP address information for each host written above that host as well. And over here on the left, I've got a couple of tables regarding the MAC address tables that each of these switches has. And what we get to do is we are going to start with clean tables, meaning nothing in those MAC address tables, and also the PCs with no ARP cache entries. So we'll clean them all so we're from a fresh starting state. We'll generate some traffic individually, and then we'll predict what we expect the MAC address tables to be on the respective switches. Also, I want to point out that to build this scenario, it was not as easy as I had hoped, because a normal PC, like a Windows computer or a Linux box, they are spitting out frames of data all the time for lots of different reasons. So to get this to be a really clean and steady environment, I'm using 6 computers here that do nothing until you ask them to do something. So there's no chatter in the background from any of these PCs that might inadvertently send a frame into the network and skew our MAC address tables on either of these switches. So for our first scenario, and let's go ahead and just do this one set of traffic, a ping request from PC1 over to PC2, from here to here. So let's consider this together. If PC1 wants to go ahead and ping 10.100.0.2 on that local network, if it doesn't know the layer 2 address for PC2, PC1 is going to send out an ARP request. That's going to be a layer 2 broadcast. And that's going to go into the switch here. And so at that moment, switch 1 on gig 0/1 is going to learn the MAC address of PC1. So its MAC address ending in 6801 is going to be learned on gig 0/1. And that's an access port that's currently in VLAN 100. So it'll know that that MAC address is associated with VLAN 100. That ARP broadcast is going to go out gig 0/2, and it's also going to be sent out the trunk, which is going to be received over by switch number 2. And at that moment, right there, switch 2 is going to learn about the layer 2 MAC address of PC1. So here on the MAC address table for switch 2, on switch 2's gig 1/0 interface, it would have learned about the MAC address of PC1, which is 6801. And here's my question. Does switch 2 over this trunk, is it going to know what VLAN that frame was associated with? What do you think? And if you're saying, oh yeah, Keith, we're doing 802.1q trunking, as we talked about in a previous nugget, and as a result, there will be a tag indicating what VLAN that's for. And you're absolutely right. And as a result, switch 2 would associate that MAC address with VLAN 100. So we have 2 entries regarding inbound frames on those switch ports. And then just to complete the discussion, that broadcast would be forwarded out all the other ports associated with VLAN 100, which would go out here. So that's our initial broadcast frame from PC1 and where it goes. Next, we'd want to consider the ARP reply message. So when PC2 gets that ARP request, because it owns the IP address being looked for in that ARP request, it's going to reply. And we'll put that response in red. So the reply is going to go back into the switch. And at that point, at that moment right there, switch 1 is going to learn the MAC address of PC2 on port gig 0/2. So we have gig 0/2, the MAC address of PC2 ending in 6802, and it's also associated with VLAN 100. That ARP reply is sent to the specific address of the requester, which was PC1, so the switch, who now knows where the MAC address ending in 6801 is, would forward that ARP reply out port gig 0/1 over to PC1. And that is just the ARP request and reply. Next, we have the actual ping, the ICMP ping request and ping responses between PC1 and PC2. And let's use a green color for that. So the ping request would go from PC1 into the switch. The switch already knows about PC1's MAC address. And because the layer 2 destination is PC2, the switch knows exactly where that host lives, and it would forward that frame out gig 0/2 to PC2. And then the reply to that ping would go from PC2 back to PC1. So based on all of that traffic, the MAC address tables on the switches regarding PCs should look something like this. There's also some communications that are happening directly between these two switches, and they also have MAC addresses on their respective interfaces. So we might have an additional MAC address from switch 1 that's learned by switch 2 and vice versa. And those will show up as being in VLAN 1. We can know that that may happen. However, our focus for you and I in this exercise is to take a look at just the MAC addresses regarding PCs and hosts that these switches are adding to their MAC address tables. In a previous video, we took a look at some predictions regarding network traffic and what the MAC address tables would look like on some switches. In this video, you and I get to verify, or at least see, if our predictions were correct. Here in the top, we have switch 1, and in the bottom, we have switch 2. And these are Cisco switches, and to make it a little bit easier and more direct, I've created a few aliases. So if we do the command show alias and press enter, I've created an alias called clean. So what that basically means is if we type in the word clean, it's automatically going to execute the command clear MAC address table dynamic, which will remove any previously learned dynamic MAC addresses from the MAC address table. Also, I created a little alias called SMT for show MAC address table. And on this switch, if I type that alias name, it'll issue the command show space MAC space address dash table on this Cisco switch. And that'll help us focus on the prediction of our MAC address tables rather than having to type that out in full each time. So starting on switch 1, we'll go ahead and issue the command clean, which is clear MAC address dash table space dynamic. And we'll do the same thing on switch 2. And then we'll do an SMT just for grins on each one for show MAC address table. So we're starting off with a clean slate. Next, let's go over to PC1, clear its ARP cache, and then do a ping from PC1 over to PC2. So here on PC1, we'll do a clear ARP. Now on these virtual machines that I'm running, that's the command to clear the ARP cache. So the command to clear an ARP cache on a local computer is going to vary based on the device you're using, whether it be Windows or Linux or some other platform. So if we do a show ARP, the ARP cache or the ARP table is empty on this device. And let's go ahead and do our ping. So we're going to ping over to PC2 at 10.100.0.2. Press enter. That looks fantabulous. Let's go take a look at our MAC address tables on both switch 1 and switch 2 and see if our predictions were correct. So here on switch 1 and switch 2, we'll hit the up arrow key to do the show MAC address table command. And let's verify. So we have two entries for VLAN 100. One is PC1, one is PC2. They are both dynamically learned, and PC1 was learned on gig 0/1, and PC2 was learned on gig 0/2. And that's exactly the prediction that we had, based on looking at both the ARP request and reply, as well as the ping request and reply. And then on switch 2, we have one dynamically learned MAC address. That is PC1's MAC address right there. It was learned on switch 2 on its gig 1/0, which is the trunk interface. And because it came in with an 802.1q tag saying this broadcast, this ARP request, was associated with VLAN 100, switch 2 knows that that MAC address is associated with VLAN 100, and it can be reached off that gig 1/0 port. So, my friend, here's what's next. I would like us to take each of these scenarios independently. So we'll call them A, B, and C. And with each one of them, imagine having clean MAC address tables with nothing in them, and also the PCs with no initial ARP cache entries at all. And then, based on the traffic from PC1 to PC4, predict what the MAC address tables will be on switch 1 and 2. And then, starting again with clean ARP caches and clean tables, do that same scenario for situation B, and then once again for situation C. And then what we'll do together in a separate nugget, we'll walk through the logic of those three additional scenarios, as well as the implementation and verification that our predictions were correct. In this, we're going to take a look at additional scenarios regarding certain types of traffic going through a switched network to predict what the MAC address tables look like on the switch after that specific traffic is sent through the network. And for this scenario, let's predict what the MAC address tables would look like on the switches when we do a ping from PC1 to PC4. We're starting off with clean MAC address tables and clear ARP caches on all of our devices. And as the switch is building these tables, we know it's building it based on the source MAC addresses in frames as they come into the switch. So in this discussion, we can just focus on traffic going into the switch. So a ping from PC1 to PC4. So PC1 is here, PC4 is here. They're in the same VLAN, and we have a trunk going between the two switches. If PC1 doesn't know the layer 2 address of PC4, it's going to do an ARP request, and that traffic would go in on this port right here on the switch, and that would be one of our entries in the MAC address table. It'd be the MAC address of PC1 ending in 6801 that's reachable off gig 01 on VLAN 100. So it's going to be VLAN 100, MAC address of PC1 ending in 6801, and that's on gig 0/1. That traffic would also be forwarded over to switch 2. It would be received on gig 1/0, and so on gig 1/0 on switch 2, it would also know about the MAC address of PC1 ending in 6801, which is in VLAN 100 because of the 802.1q tag that switch 2 saw on that frame as it came in. And then when PC4 responds with an ARP reply, that's going to go into the switch here on gig 1/1. So that's gig 1/1 right there. That's the MAC address of PC4 at 6804. And that access port, gig 1/1, is in VLAN 100. And because switch 2 is forwarding a frame destined for 6801, based on its MAC address table, it knows it needs to forward it that way. So it sends the frame this way. That's received by gig 00 on switch 1. So on gig 00, switch 1 now learns about the MAC address of PC4 from its source MAC address, and its MAC address is ending in 6804, and that's also in VLAN 100 because the frame going this way also was tagged with an 802.1q tag, indicating that frame belonged to VLAN 100. And then that response would make it up to PC1, and then as PC1 sends the ICMP ping request over to PC4, there's nothing new to be learned by either switch there from PC1's source MAC address, nor for the ping reply as it goes back, because switch 1 and 2 have already memorized PC1 and PC4's MAC addresses respectively. I've got some aliases in place. One of them is called clean, and if we issue that command, it'll clear out the dynamically learned addresses in the MAC address table. I've also got an alias called SMT, which will show the MAC address table. So on both switches, we'll issue the alias clean to clear the MAC address tables, and then we'll go to PC1 and do our ping. So here on PC1, we'll do a show ARP just to validate there's nothing in the ARP cache on this local computer, and we'll do our ping. And PC4 is at 10.100.0.4. We'll issue that ping, and that looks great. Now we'll go take a look at the MAC address tables over on switch 1 and switch 2. So over on switch 1, we'll issue the command show MAC address table using the alias of SMT on this Cisco switch, and we'll do the same over here on switch 2. And that indeed does match our prediction here on switch 1. So we have the MAC addresses of PC1 and PC4 respectively, both in VLAN 100, reachable via ports gig 0/1 and the trunk of gig 00. And then on switch 2, we've got the two VLAN 100 entries, one for PC1, one for PC4, reachable off of the trunk on switch 2, and on switch 2 the local port of gig 1/1 to reach the MAC address of PC4. We also dynamically learned a MAC address ending in DE00, and that's a MAC address over on switch 1 on its trunk interface that had generated at least one frame of traffic on its own, and that's why it's showing up here. It's not related to our VLAN 100 traffic, but indeed this MAC address is showing up, and that's the reason why. For this scenario, we're going to generate some traffic within VLAN 200 going from PC3 over to PC5, but before we do that, we'll predict what the MAC address tables would be on both switches that are connected via a trunk, and then we'll validate it via a demonstration. So here's our task, to predict the MAC address tables on switch 1 and switch 2 after a ping from PC3, which is right here, going over to PC number 5, which is right here. And I thought to myself, you know what, Keith? That's what I call myself. I should probably give a moment right here for a person who wants to solve this on their own a chance to do it. So if you want to solve this on your own before we do the walkthrough, hit pause, solve it, and then we'll continue together. So if PC3 does not have an entry in the ARP cache for the MAC address of PC5, it's going to send an ARP request as a broadcast. It's going to come in on port gig 0/3 right here on switch 1, and that's an access port in VLAN 200. And the source MAC address in that frame is going to be PC3's source MAC address ending in 6803, just like that. Because that's a broadcast associated with VLAN 200, switch 1 doesn't have any other access ports at the moment in VLAN 200, but it does have a trunk that's associated with and carrying VLAN 200 traffic. So switch 1 tags that frame with an 802.1q tag, marking it as VLAN 200, and sends that broadcast over the trunk where it's received by switch 2. Switch 2 on gig 1/0 looks at that source MAC address, which is 6803. Still PC3's source MAC address. It had the 802.1q tag saying it came from and is associated with VLAN 200, and switch 2 would forward that broadcast out to all other ports associated with VLAN 200, which would include gig 1/2 and 1/3. So both PC5 and PC6 listen to that broadcast, they process it, but only PC5 is using the address that's in the ARP request of 10.200.0.5, so PC5 will respond back with that ARP reply. And that goes into the switch on port gig 1/2. So we'll add that port here, where switch 2 now knows the MAC address of PC5, which ends in 6805. And that's associated with VLAN 200 because the access port gig 1/2 is associated with that VLAN. And that reply is sent back to the MAC address of PC3, which ends in 6803, which the switch knows where that is, so it forwards it out this way, also tagged with an 802.1q tag indicating it's associated with VLAN 200, which is received by switch 1, who looks at the source MAC address, which ends in 6805, adds that to its MAC address table, associates that with the port where it learned that on, which is 0/0, and due to the 802.1q tag, it knows that that MAC address is associated with VLAN 200. So if these entries didn't exist previously in the MAC address tables, after a ping request from PC3 to PC5, we would expect at least these entries to have been added as a result of that network traffic. So starting off on PC3, let's do a show ARP, and let's do our ping over to PC5, which is over at 10.200.0.5, and press enter. That's looking great. Let's go back over to our switches and verify our predictions regarding the MAC address tables. So here on switch 1, we'll do a show MAC address table, and then we'll do the same command down here on switch number 2. Show MAC address table and press enter, and that confirms what we expected. So we have VLAN 200 for all the entries that we just dynamically learned. Switch 1 believes that 6803, that's PC3's address, is reachable on its local port of gig 0/3, which it is. It also believes that the MAC address ending in 6805, which is PC5, is reachable over its trunk gig 0/0, which is also accurate. And I say that as if, well, the switch is accurate. No, our predictions were accurate. That's the even more important part. And then down on switch 2, it indicates that 6803, which is the MAC address of PC3, is reachable over the trunk on switch 2 of gig 1/0, which it is, and that the MAC address 6805 is reachable on the local port of gig 1/2 on switch 2. And so that validates our predictions regarding the MAC address table entries that were dynamically created as a result of the specific network traffic between PC3 and PC5. And here's what I'm going to invite you to do. I'd like you to take this final scenario, which is a ping from PC1 to PC2, which we've done previously on its own, but combine it with a ping from PC3 to PC5, which we just did. And as a result of both those elements happening, the entries that we would expect to see, and to reinforce the results after you make your predictions, you can go back to those previous nuggets where we generated that specific traffic just to verify that your predictions match up with what the switch is delivering. Oftentimes, we're going to want to have redundancy inside of our networks. And in the world of switching, that might equate to having more than just one path. So if PC1 wants to talk to PC4, well, if this link goes out, by having a redundant path already in place, that redundant path can still be used. However, in the world of switching, if we do have parallel paths, consider a broadcast. A broadcast, maybe an ARP request that PC1 sends into the switch. That broadcast is forwarded out the trunk, received by switch 2, forwarded out the trunk, received by switch 3, forwarded out the trunk, received by switch 1 again, who then forwards it, and that could cause a switching loop, a layer 2 loop caused by a single broadcast initiated by a PC on a VLAN. Well, because it's not desirable to have frames that just loop forever on the network, we have a protocol named Spanning Tree Protocol, whose job it is to identify parallel paths on a layer 2 network, and then wherever there are redundant paths, to go ahead and logically block on ports so that there's only one path through that network at any given time. And to perform this quote-unquote magic of identifying parallel paths and blocking them, the Spanning Tree Protocol sends and receives little BPDUs. That stands for a Bridge Protocol Data Unit, which, in the world of Spanning Tree, is the language of love. It's how these switches can communicate and talk to each other regarding the spanning tree and which ports should be forwarding and which ports should be blocked. And during that process, one of the switches is going to be identified as the root. Think of it as the King Kong of the spanning tree topology. And it's referred to as the root bridge. And the reason it's called a root bridge is because when this was implemented or developed many, many years ago, we had bridges, layer 2 switching devices called bridges. Now we use switches instead of bridges. However, the term is still referred to as the root bridge for the King Kong of the spanning tree topology. You can kind of think of the root bridge as the winner. And as a result of winning, the root bridge is given the opportunity of forwarding on all ports for that VLAN. In this case, we're looking at the VLAN 100. So if switch 1 is the root bridge, the winner of the spanning tree, who are the losers? Well, they're not quite losers, but they're simply switches, other switches that didn't become the root bridge. In our topology here, that would be switch 3 and switch 2, which are the non-root bridges. And by using BPDUs, switch 2 and switch 3 can identify what is the optimal or fastest path to reach the root. And in this topology, it would be switch 2's gig 1/0, so that would be put in a forwarding state, and switch 3's gig 0/1, and it would be put in a forwarding state. And also, those ports that are the fastest path to get to the root, those are referred to as root ports. And then when it comes down to this segment between switch 3 and switch 2, if both these ports are forwarding, we're going to have a loop. So switch 2 and switch 3 are also going to have a little face-off and duke it out. They're going to be sending BPUs back and forth to determine which of these two switches ports should be forwarding and which should be blocking. And if switch 2 wins, it's going to go ahead and be forwarding on its port, and switch 3, if it lost for this segment, would go ahead and block from a spanning tree perspective on that port. So any frames that do come in to gig 0/2 from switch 2 would simply be dropped, put in the bit bucket. And also, if this port is blocked, switch 3 is not going to be forwarding any data frames out that port up to switch 2. And spanning tree is going to keep that block in place until there's some kind of other change in the network. An example would be this path between switch 1 and switch 2 fails, or the cable's cut, which would also cause that path to fail, and then spanning tree could reconfigure the topology and then start forwarding on this port and take advantage of the additional links that are in the network to forward traffic. But that's the basic concept of spanning tree, to identify parallel paths in a layer 2 network and then block on one or more ports so that we don't have the possibility for a layer 2 loop to happen inside of our switched network. It's often fun to verify what we think is happening in a network. So what I'd love to do in this nugget with you is take just a moment and take a look at a spanning tree topology in our current network for VLAN 100, and then cause a network failure in one part of our network, and then see the results of spanning tree adapting to that failure and choosing an alternate path to go ahead and forward frames through. So here's our current topology. We're going to focus on VLAN 100 for this discussion. So the switches have all shared their BPDUs with each other, and as a result have chosen the lucky winner, which is switch 1 to act as the root bridge. And the way the winner works with BPDUs is the bridge that has the lowest, like a golf score. The lowest bridge ID becomes the winner of the election for the root, and that's how that happened here on switch 1 as well. And as a result, switch 1 for VLAN 100 is forwarding on all ports associated with VLAN 100, including gig 01, 02, 00, the trunk, and gig 1/3, the other trunk. Switch 2 and switch 3 both have one root port, respectively. That's this guy and this guy, which are both forwarding frames. But over here on this segment, switch 2 is forwarding frames on its gig 0/3. In this topology, we only have a single block port, and that is switch 3 on gig 0/2. Everything else is in a forwarding state with spanning tree. So what we'll do is we'll go in, we'll verify that everything's forwarding for VLAN 100 except for that one port, and then what we'll do is we'll go ahead and we'll simulate a failure by shutting down one of these interfaces between switch 1 and switch 2. Spanning tree will recognize that change, and it'll move this interface right here on switch 3 out of the blocking state and move it into the forwarding state so we still have connectivity through the network. Before we make any changes, let's take a look at the current state. And to do that, we're going to issue the command show space spanning-tree space and then add VLAN space 100 on this Cisco switch. In fact, I'm going to send this command to all three switches simultaneously so we can focus on the results. So we'll send that command to each of our three switches, and let's take a look at the results. So here on switch 1, regarding VLAN 100 and its four interfaces that are involved with VLAN 100, notice here that the forwarding status on all of those ports from a spanning tree perspective is that it's willing to forward traffic. And that's partly because this switch, switch number 1, won the election, and this switch is the root for the spanning tree. Let's take a look at switch 2. Over here on switch 2, using the same command. So here on switch 2, we have gig 11, which is the port that's going up to PC4 in VLAN 100. And we have two trunks. We have gig 10, which is the trunk over to switch 1, and gig 0/3, which is the trunk over to switch 3. And all three of those ports are in the forwarding state, not being blocked. It's also indicating here that the root port on switch 2, that's the port that's the fastest path to get to the root bridge, is gig 1/0, which based on our topology, it is. But somebody's got to be blocking, so That's going to be switch 3. Let's go take a look at switch 3. So here in switch 3, gig 0/1, which is the port that connects over to switch 1, it's in a forwarding state. It's also the root port, the fastest path from switch 3's perspective to have access towards the root. We can also see that 0/2 here is in a current blocking state. And it's because of that one port in this topology that's blocking due to spanning tree that's preventing a layer 2 loop. So let's simulate a failure of a link between switch 1 and switch 2. And what we'll do is we'll go to switch 1 and we'll simply shut down the gig 00 interface, which will stop this root bridge from being able to send BPDUs over to switch 2. And it'll also remove the parallel path. And as a result, the spanning tree topology is going to change, and it's going to move gig 0/2 on switch 3 into a forwarding state. And that's a real focus regarding the change that we want to verify in this demonstration. So back on the switches, let's go over to switch number 1. We'll go into configuration mode on the Cisco switch. We'll go into interface configuration mode for gig 0/0, and we'll use the command of shutdown to go ahead and bring that interface down and out of commission. And then based on the version of spanning tree we're using and how it's tweaked, the actual change from a spanning tree topology could take anywhere from a few milliseconds up to many, many seconds. So we'll give that a moment to settle, and while it's doing so, we'll go over to switch 3. And here in switch 3, when we run this command again, show spanning tree for VLAN 100, we'd expect to see gig 0/2 no longer to be blocking, but rather to be forwarding. And with traditional spanning tree, IEEE's 802.1D as in David, that's the actual spanning tree protocol, the original flavor. And it does take a few seconds to converge. And this port, gig 0/2, is going to go out of blocking state. It's going to go into something called listening state. It's then going to go into learning state. And then eventually forwarding state once it knows the coast is clear and there are no loops in the layer 2 topology. So what we'll do here is we'll hit the up arrow key, do a show spanning tree for VLAN 100 again, and focus on the change. And that is that gig 0/2 used to be in blocking state, but it's now in forwarding state because spanning tree realized there's no longer parallel paths, and as a result, it didn't have to put any of the ports in the topology into a blocking state. When putting a network together, or at least when designing a network, an ideal one, we'd have some features there that we wanted for functionality, some would be there for security, and some would be there for convenience. And as we consider this topology, we have lots of moving parts here. We've got some layer 2 switches right here, switch 1 and switch 2. It looks like we have a connection in between them. It's very likely a trunk. And then we have some connections going out to computers and printers. Those would be access ports assigned to a specific VLAN. And all of these devices over here could be considered logically to be on the inside of our network. To the left, if you will, of this firewall, providing some security measures between the inside of the network and everything else. And out here on the right-hand side of the firewall, we could consider all of this to be the outside. And one general rule of thumb is that we don't want individuals on the outside to have access all the way to the inside of our networks. So the firewall can help enforce those rules. But at the same time, we may have some customers that need to get to some of our servers. And so if we're not allowing individuals on the outside to go to the inside, where do we put them? And one option would be to create a DMZ, which is an acronym for a demilitarized zone. It's not the inside, it's not the outside, it's somewhere in between. And then we have some security rules which allow users on the internet, for example, to access specific resources on servers in our DMZ. We also have routers involved, and what routers do for a living is they forward traffic or packets based on the logical layer 3 addressing. So while switches forward frames inside of a network at layer 2, a router is looking at layer 3 and making forwarding decisions based on that layer 3 information. And this device right here is a wireless radio that allows wireless devices like Computer 3 to connect to our network. And this is referred to as an access point, or an AP for short. And one of the challenges with putting in an access point is that if we put it inside, for example, a ceiling, or we mount it to a ceiling, not only do we need an Ethernet connection to connect the access point to the physical switch, but we're also going to need some power for that access point to drive the radios inside of that access point. So a couple options exist. Number one, we could have a separate little transformer that we plug into an outlet and plug into this access point, but that becomes very ugly and also a little troublesome to find an outlet very close to the access point wherever you want to put it. Another option is to include the power from the actual switch and deliver that power over the cable that goes over to the access point. And that concept of delivering power from the actual switch over the Ethernet cable that goes to the access point, so we have data and power going over the same cable set, is referred to as PoE. That's power over Ethernet. And there's more than just one standard for it. There's PoE and there's PoE Plus, and it's the IEEE that has set some standards for us regarding power over Ethernet. And that way, if you have a switch that's compatible with standard X, and you have an access point that's also compatible with that standard, you could use those two devices together, even though they're both perhaps made from a different manufacturer, as long as they're both following the standard. And besides access points, there's lots of other potential opportunities for power over Ethernet devices, including IP telephones, or IP-based cameras, or other devices that need power that can receive that power over the cable. And some of the standards from the IEEE regarding power over Ethernet include 802.3AF, AT, BU, and BT. There's different applications. Some are designed to give lots and lots of power, while others are designed to be energy efficient, and they can range from about 15 watts to 100 watts, depending on the type of technology and the type of standard that's being used. And the two primary standards that we're going to see out there most frequently are 802.3AF, which is commonly referred to as power over Ethernet, and 802.3AT, which is often referred to as power over Ethernet plus. And that's a huge convenience factor by only having to plug in one cable, a network cable, to a device to be able to send and receive data from that device, as well as to give that device the power that it needs to run. Sometimes it's handy to get a copy of packets so that we can analyze or take a look at them. In this, I'd like to chat with you about a concept called port mirroring, where we can take the packets and frames from one area of our network or one port on a switch, and then forward those to another port where we can take a closer look at them. So here's our topology. And let's say the scenario is that this server right here, which is connected to gig 0/4 on switch 2, is having some problems with network connectivity, or it's not operating correctly. And so we want to take a look at all the packets on that port so we can take a closer look. Well, how do we go about doing that? Well, one way is we could install some software on this server to actually take a look at those packets. However, that's going to interrupt the server, because it's also going to have to process the packet analyzer to capture those packets. Another option is we could do port mirroring, which is to tell the switch, "Dear Mr. Switch 2, please take all of your traffic that's going into or out of gig 0/4, and let's send a copy of all of those packets and frames over to another device where we can analyze those packets." And so for our discussion, let's choose computer 2 as the lucky winner, the recipient who's going to get a copy of all the traffic that goes in and out of gig 0/4. So from a switch perspective, we need to first of all identify, where does computer 2 live? Where is it connected? And computer 2 is connected to this port right here, which is gig 0/2. So depending on the vendor's equipment, we'd configure the switch 2, to copy the packets from gig 0/4 and send a copy of all that traffic to the destination interface of gig 0/2. At which point, computer 2 would need to be running some software or something that could look at all those packets so we could analyze them. So in a Cisco environment, when we're doing the mirroring, the port mirroring on a local switch, they refer to it as SPAN, which is an acronym for Switched Port Analyzer. And even within a specific vendor, based on the hardware and the version of software that's being used on that switch, the commands could also vary. So here's an example of the commands we could use on a Cisco switch. Monitor session and a number. For example, session number 1, which is just identifying that span session in the switch, and we use the source keyword and then specify interface gig 0/4. That's where we want to pull the data or the frames from. And then the second line is to specify where we want those copies of the frames to go. And we use the command monitor session 1 destination, and then the interface where our monitoring device is that's going to collect those packets. In this case, it's the Windows machine, computer 2, on port gig 0/2. And that would cause the switch 2, to take all the frames on port gig 0/4 and mirror them or copy them over to gig 0/2 for analysis. Taking a look at the concept of port mirroring and how it can be used to copy packets from one area of our network over to another for analysis. I hope this has been informative for you, and I'd like to thank you for viewing.
Thanks for watching our second, and press the button below, like, subscribe, and bell icon.